Hello, this is Brett Lucht again, and today's lecture will be on the solid electrolyte interface on the anode. So the first two lectures were primarily covering aspects of general lithium-ion battery chemistry. The first lecture was an overview of lithium-ion battery chemistry as a whole, and the second lecture was a focus on electrolytes for lithium-ion battery, which is what my focus area of research is. Today's lecture will focus on research that has been conducted in my research group with a focus on the understanding of the solid electrolyte interface on, the lithium-ion battery on the anode. And so with that, we will get started here. Let me share the screen. Okay, and so what we're going to be talking about today is the generation and evolution of the solid electrolyte interface on lithium-ion batteries. So as we've already gone over the last couple of lectures, the lithium-ion battery is composed of three primary components. The lithiated metal oxide cathode, which is the source of the lithium metal, the graphite or other material anodes, such as silicon and lithium, and we'll discuss all three different anode materials today, and the electrolyte, which is predominantly lithium hexafluorophosphate and a blend of carbonate solvents. So during the first formation cycle of the lithium-ion battery, the solid electrolyte interface is generated on the surface of the anode. This solid electrolyte interface is a composite material or a conglomeration of material, of mosaics, of different compositions, which has been studied for a long time, since 1979. And there are many different proposed compounds that are in this solid electrolyte interface. And then also there have been multiple proposed reduction patterns or different possible routes that these species have been generating. So today what we're going to do is go over two different things. One is basically, what is the SEI? What's the composition of the SEI? And then really, how does the morphology of the composition, morphology of the SEI relate to the composition? And are both of these two things, which they are, both of these two things are important to the overall function of the solid electrolyte interface. So with that in mind, this solid electrolyte interface has been mentioned multiple times in my previous lecture. The SEI results from the reduction of the electrolyte, which once again predominantly includes lithium hexafluorophosphate and ethylene carbonate as the two compounds that are basically in all commercial lithium-ion battery formulations. Outside of that, there's frequently dialkyl carbonates and various additives such as VC and EPC, but ethylene carbonate and LiPF6 are fundamentally present. The formation mechanisms are not really fully understood, and we're going to discuss a lot of those formation mechanisms today, and on the changes, how the surface changes on lithium and silicon. We're also going to go over how the SEI thickens, and it's known to thicken, and this has been reported by many research groups, but this mechanism is not very well understood, and in today's lecture, we're going to propose a new mechanism for how the SEI thickens. Another really important aspect in terms of understanding the SEI is that many different groups have reported many different compounds. And so there's a certain level of complexity with the solid electrolyte interface because there's a lot of different species that are present in it. And because of this, a lot of researchers just say, well, it's really complicated, we can't understand it that well. So one of the things that we have done over the last decade is we've gone back and tried to individually address the different roles of the different components of the electrolyte. We want to understand what the role of the salt is, what the role of the solvent is, and also separately what the role of the additive is in both the SEI formation, in the structure, and in the evolution. And we've gone back, and what we've done is basically over the last decade conducted a systematic investigation. And how have we done this? We've done this by isolating each component of the electrolyte and studying its individual contribution to the SEI formation and then evolution. And then one of the other things that we've spent a lot of time doing is really conducting an analysis with as many different possible techniques. And so what we really want to do is we don't want to focus on just one analytical technique, such as XPS, X-ray photoelectron spectroscopy. We want to use XPS coupled with SEM and maybe TEM and EDX and IR, because the more different analytical techniques we can utilize, and if these different techniques agree with each other, then we have that much more support for our understanding, and we have that much more confirmation that the species that we think are present and the species that we think are important to the function are actually there. So with that in mind, we'll go back to some research that we published in 2013. And in this particular study, we conducted an investigation of just LiPF6 NEC. Now, we went back and used this simplified electrolyte, only 2 components, to simplify the composition of the SEI. Because one of the challenges with the electrolyte is when you have an electrolyte that has 3 or 4 different components, each of those components is going to contribute to the compounds that are present in the SEI. And if you simplify the number of components and you still get a functioning cycling battery, then what those components are, they do comprise a valid SEI. And in this case, many researchers have reported that EC is the central component, the most important component in SEI formation. And so that's why we use the simplified electrolyte of LiPF6 NEC. And what you can see is this is an example of TEM images of graphite anodes extracted from cells as we slowly start to drop the potential on the first charging cycle. And what you see is we start off this nice, crisp, clean edge of graphite. And as we drop the potential to 1.3 volts versus lithium, where we start to generate an SEI, we start to see a film on the surface of the graphite. And this film is primarily composed of oxygen and fluorine. As we continue to drop the potential, this surface film gets thicker and thicker until we go all the way to 0.05 volts, which is the ending point of the charging cycle. And basically what we have is a surface film which is roughly 30 to 40 nanometers thick. Now what's interesting is if we put an additional 10 cycles on this cell, the thickness of this film doesn't really change significantly. And I'll also point out that as we go along all of these surface films, what you can see is that the surface film has roughly a 1-to-1 composition of oxygen to fluorine. From the very beginning to the very end on the outside. What this suggests is we're getting a relatively uniform composition of the SEI, at least on the first cycle, from the inner SEI, the first part that's formed, to the outer SEI that's at the end of the cycling. And from a combination of XPS and IR spectroscopy, what the composition of this solid electrolyte interface is predominantly lithium ethylene dicarbonate, the species here, LEDC, along with lithium fluoride. Now, some collaborative work that we conducted with Hubert Gastiger at TU Munich, we conducted some online electrochemical mass spectroscopy of these same electrolyte formulations, LiPF6 and pure EC. And in this case, we see the gases that are evolved during the first charging cycles. We charge the battery and then discharge, and then charge and then discharge, basically on multiple cycles. And what we observe is on the first cycle, we observe ethylene gas generated, and that's really the only gas that is observed, nothing else. And so with this in mind, basically the combination of online OEMS and XPS and SEM and TEM and IR spectroscopy reveals that basically the first cycle, the initial formation cyclings for a electrolyte, which is composed of EC and LiPF6, the predominant reaction which is occurring is ethylene carbonate is being reduced to generate lithium ethylene dicarbonate, excuse me, along with ethylene gas. And then the LiPF6 is being reduced to generate lithium fluoride, along with low concentrations of lithium fluorophosphates. So what this tells us is this SEI, the simple electrolyte, the simple SEI from a simple electrolyte composition is predominantly composed of lithium ethylene dicarbonate and lithium fluoride and is approximately 50 nanometers thick. Now I'll point out, In this particular depiction that we published back in 2013, we showed the structure of this SEI is kind of a solid solution, where the lithium fluoride is intermingled with the lithium ethylene dicarbonate. However, at the time, we didn't really have evidence for or against this. This was just how we depicted the diagram. However, one real question is what is the nanostructure of this material? Is it as shown here, where we have a kind of a uniform blend of lithium fluorine and lithium ethylene dicarbonate, or do you have nanostructured areas of lithium fluoride and nanostructured areas of lithium ethylene dicarbonate? And so this is something we'll address further along in the presentation. So another really fundamental problem and question in lithium-ion battery chemistry was something that I mentioned in the second lecture on electrolytes, which is that there's a fundamental difference between the cycling performance of ethylene carbonate-based electrolytes and propylene carbonate-based electrolytes, despite the fact that these two species are very, very similar in structure. There's just a single methyl group that's different, that differentiates these two species. Now, the other thing is that in general, propylene carbonate would be viewed as the superior, the better solvent to utilize as an electrolyte composition, because it has a much lower freezing point than does the ethylene carbonate. However, when you look at the 1.2 molar solutions of LiPF6 in propylene carbonate, what you see is on the first cycle, instead of going down and seeing the stages of lithium that we observe typically, we see continuous electrolyte reduction. Now, what was interesting was Professor Abe's research group back in 2008 published this very interesting study that showed that there was a concentration dependence. And if you increase the concentration of the LiPF6 salt, that instead of seeing continuous electrolyte reduction and continuous exfoliation of the graphite, you could get propylene carbonate-based electrolytes to both intercalate and then de-intercalate reversibly with lithium metal. And so we thought this was really interesting, that you, just by changing the concentration of the salt and nothing else, this is pure, these are once again simple electrolyte formulations, just PC and LiPF6, but yet it changes the cycling performance as a function of concentration of salt. So when we went back and we looked at these surfaces of the graphite electrodes, which once again, I didn't point this out originally, these are binder-free graphite electrodes. So these are just graphite particles. There's also no binder. So once again, we're trying to avoid any complications of characterization. Now with this, we start off, we've got the nice, fresh, crisp, clean graphite edge. If we go to the 1.2 molar species, we kind of surprisingly don't see much of anything generated on the surface film. But then again, we're also seeing continuous electrolyte decomposition. At 2.4 molar, we start to see some kind of surface materials. As we go to the really high 3.5 molar concentration, what we can see is relatively thick surface films, except it's really very different of a surface film than what we observed for the EC-based electrolytes. These are very, very grainy surface films. In the case of the LiPF6 EC-based electrolytes, we had very, very amorphous looking films, while these are very grainy. Now, what's also interesting is when we conduct the XPS and NMR analysis, we have very high concentrations of lithium propylene dicarbonate, especially when we have low concentrations of salt. However, when we go to high concentrations of salt, we have very, very high concentrations of fluorine. Now, what you can see here is in terms of the surface films, we have very, very high concentrations of fluorine and very low concentrations of oxygen. So if you recall from the EC-based electrolytes, we have roughly a 1-to-1 ratio of oxygen to fluorine, while here we have dramatically more fluorine than we do in terms of the oxygen. What this suggests is that we have a very different composition of the anode SEI. And in particular, what it suggests is that at high concentrations of salt, we have predominantly lithium fluoride in the SEI with very low concentrations of lithium propylene dicarbonate. What this also suggests is that while we see very high, lots of electrolyte reduction and decomposition at 1.2 molar, we don't observe very much of it here. And I'll point out that we do rinse these electrodes to remove the residual electrolyte. And what we believe is occurring is that the lithium propylene dicarbonate has much greater solubility than lithium ethylene dicarbonate. So one of the fundamental differences here is the solubility of the SEI species, is that in order to generate an SEI species, the species must be deposited on the surface and stay there and not be dissolved away. So if we go back and we try and understand what the difference is as a function of salt concentration and why our SEI is changing as a function of salt concentration in these propylene carbonate-based electrolytes, what we can see is if we look at the IR spectra, we see free PC in solution. As we increase the salt concentration, all of a sudden there's no longer any free salt and free solvent, and we only have propylene carbonate, which is consistent with being bound to the lithium salt. And we see the same thing in case of the PF6 region, where when we start off, we have PF6 being very symmetrical, suggesting that the PF6 is not bound to the lithium cation. And then at high salt concentrations, as PF6 signal changes, consistent with PF6 being bound in a contact ion pair. The similar results are observed from the DOSY NMR, which suggests that PF6 diffuses twice as fast at low salt concentration, while the diffusion rate is very similar for lithium and fluorine at high salt concentrations. What all of these results suggest is that there's a change in the solution structure of the electrolyte upon a change in the salt concentration. And at low salt concentrations, we have a solvent-separated ion pair, and at high salt concentrations, we have a contact ion pair. Now, what this means for the overall SEI generation is that basically when we have low concentrations of LiPF6, we have the solvent-separated ion pair, and under these conditions, the predominant reduction species is lithium propylene dicarbonate. The lithium propylene dicarbonate is still relatively soluble in the electrolyte, and so isn't deposited on the surface and doesn't generate a passivation layer. Alternatively, at high LiPF6 concentration, we have the primary species in solution being this lithium PF6 contact ion pair. And under these conditions, the predominant species being generated by the reduction process is lithium fluoride, which is insoluble in the electrolyte and passivates the surface. So going back and trying to develop a better understanding of these electrolyte reactions, these reduction reactions on the surface of the anode, we went back and utilized a fundamental physical organic analysis method, which is we utilized lithium naphthalide, which is a very good one electron reducing agent, to try and synthesize independently all of these SEI components. And if you also look at this lithium naphthalide, it looks structurally similar to the graphite surface. And it has a very similar reduction potential to lithiated graphite. When we take the lithium naphthalide and add it to ethylene carbonate, we generate lithium ethylene dicarbonate along with ethylene gas quantitatively, basically in 75, 80, 90% yield, very, very high yields. And this is the only species we observe by proton NMR spectroscopy. These are THF, which is the solvent we do the reaction in, and then also residual water because we do the NMR spectrum in D2O. We do the same reaction with propylene carbonate, and we generate only lithium propylene dicarbonate and propylene. Very, very clean reactions. If we go to diethyl carbonate or dimethyl carbonate, these reactions are a little bit more complicated, and we see lithium ethylene dicarbonate along with lithium ethoxide and carbon monoxide. But nonetheless, these reactions are much smaller than the reactions of EC and PC in terms of the generation of the solid electrolyte interface. Now, if we go back and do a similar reaction in terms of the reduction of lithium hexafluorophosphate, and we take lithium hexafluorophosphate and add it to lithium naphthalide, what we generate by XPS spectroscopy is very, very high concentrations of lithium fluoride, along with low concentrations of lithium fluorophosphates, LiXPOYFC, along with low concentrations of lithium fluorophosphides. Similar species are observed by NMR spectroscopy, the lithium fluorophosphates, but I'll also point out that under these conditions, there's really not any available oxygen for reaction of the lithium fluorophosphide to generate lithium fluorophosphate, which in the case of when the presence of carbonate solvents, you would not typically see these lithium fluorophosphides and just the lithium fluorophosphates. But nonetheless, the main aspect of this overall reaction is that the predominant species generated is lithium fluoride, far more than any other species. So with this in mind, this brings us back to the overall reduction reactions to generate the solid electrolyte interface. So as I've already said, if you have ethylene carbonate, you predominantly make lithium ethylene dicarbonate and ethylene. This is the dominant solvent-based reduction reaction. If we have dialkyl carbonates, we also will generate low concentrations of lithium alkyl carbonates along with lithium alkoxide and CO. And with LiPF6, we generate predominantly lithium fluoride with low concentration of lithium fluorophosphates. So this brings up the question is, why is the SEI so complicated? If we go back and do the simple reduction reactions of the fundamental components of the SEI, we get a relatively non-complicated mixture of species. When we build binder-free graphite batteries and we cycle them, we see the same species on the surface during the initial formation cycle. So this brings up what happens when the batteries are aged over time. So when we have significantly more cycling. Now this was a really nice series of papers published by Argonne National Laboratory by Daniel Abraham and Christina Edstrom, who's also at Uppsala in Sweden. And basically what was observed is that upon the aging of the cell, going from fresh cells with 0% power fade to cells with 35% power fade after a significant amount of calendar life aging and cycling aging, what they observed is that the composition of the SEI changes significantly by XPS. And you start off and you have low concentrations of fluorine and high concentrations of carbon. And after a significant amount of aging, what you see is very significantly higher concentrations of fluorine and lower concentrations of carbon. At the same time, you can see very nice, crisp, clean edges of your graphite by SEM after the initial cycling, but after all of the aging and power fading, you can see very, very thick surface films on the graphite. And so it was generally known when we started this study that first, the SEI gets very much thicker upon aging of cells. And at the same point, the composition of the SEI changes from something that's predominantly organic to something that's predominantly inorganic. But overall, the mechanism of how this happens was not understood at all. So with our understanding of the fundamental initial formation cycling reactions, we wanted to go back and try and understand how this evolution reaction might also be occurring. So with this in mind, we were now able to synthesize independently the SEI components, the lithium ethylene dicarbonate and the lithium propylene dicarbonate and the lithium methyl and lithium ethyl carbonate via the lithium naphthalide reduction reaction. And if we take these species and expose them to air, water vapor for a very short period of time, the IR spectrum that are characteristic of these lithium alkyl carbonates rapidly changes to lithium carbonate after a very short period of time. So what this suggests is that these lithium alkyl carbonates are relatively hydrolytically unstable. And upon exposure to water, they're converted to lithium carbonate, CO2, and lithium alkoxide. This has been previously reported by Kang Zhu in 2006. However, it's also known that if you have CO2 present in cells, which is very frequently the case due to the fact that there are oxidation reactions that occur on the cathode side, which generate CO2 gas, that CO2 can be reduced to generate lithium carbonate and carbon monoxide. And so with this in mind, in trying to understand how these SEI components evolve, we wanted to both understand how lithium carbonate evolves and changes, and also the lithium alkyl carbonates. Because while this hydrolysis reaction is a significant problem, there's very, very low concentrations of water in the lithium-ion battery. And so the presence of these hydrolysis reactions is probably not very significant. So with that in mind, we wanted to go back and look and see how lithium carbonates react with LiPF6 in a standard dialkyl carbonate. So once again, in this case, we took lithium hexafluorophosphate, dissolved it in dimethyl carbonate, added it to lithium carbonate, and then stored the samples at moderately elevated temperatures, 55 degrees centigrade, for only 2 days. And what we observed, surprisingly, was that the lithium carbonate quantitatively decomposes over this time frame. We start off the IR spectrum of lithium carbonate, and then after 2 days, there's no lithium carbonate present whatsoever. If we look at the XPS spectra of this residual material after the decomposition, what we observe is there's low concentrations of carbon and a little bit of oxygen, but very high concentrations of lithium fluoride with low concentrations of lithium fluorophosphate. If we go back and look at the solution, the dimethyl carbonate solution by NMR spectroscopy, what we observe is a single new peak by NMR spectra, in the NMR spectra. We have the LiPF6 doublet and septet, and now we have a triplet and a doublet, which is consistent with the presence of this lithium difluorophosphate species in very clean, occurring very clean reaction. In addition, if we look by GCMS, we observe carbon dioxide gas. So in the terms of the reaction of lithium carbonate with LiPF6 and dimethyl carbonate, it's a very clean reaction. There's basically only 3 products. We generate lithium fluoride, we generate lithium fluorophosphate, lithium difluorophosphate, and we generate CO2. Now, as frequently happens when working in the field of lithium batteries, is that a lot of this work is also being conducted in industry. A lot of industrial researchers are doing similar types of reactions, and frequently they don't publish their results in the primary literature. After we observed this, we went back into the patent literature and observed that this compound had been patented and the synthesis of this compound had been patented, which occurs via this exact same reaction by researchers at Mitsubishi a few years before. And it was interesting because this particular compound, lithium difluorophosphate, is also a relatively well-known electrolyte additive, which is reported to reduce the impedance in the anode SEI. And so it's always important to recognize that a lot of the research in batteries isn't always published in the primary literature. But we were surprised by this, but shouldn't have been, because this is how they make this particular additive. So what happens if we take the lithium ethylene dicarbonate, which we already know is significantly less stable than lithium carbonate because it hydrolyzes very rapidly while lithium carbonate does not. So we take lithium ethylene dicarbonate and store it under the same conditions, LiPF6 and DMC at 45 degrees centigrade. Once again, we see quantitative decomposition of the lithium ethylene dicarbonate, and we see the generation of lithium fluoride in very high concentrations. However, instead of observing the lithium difluorophosphate, now we see a mixture of lithium dialkyl fluorophosphates along with trimethyl phosphate itself. And so this reaction instead clearly is starting to have disproportionation reactions where the dimethyl carbonate is becoming involved because we're generating methyl phosphates, and also we're generating oligomerization of our residual ethylene, the residual ethylene bridge, which can be observed by GCMS. We observe both oligoethylene oxides and carbon dioxide gas. So this is a significantly more complicated reaction. So nonetheless, if we look at this overall LiPF6 induced acid-base decomposition reactions, along with the hydrolytic decomposition reactions, what we can see is that the lithium alkyl carbonates, which are the primary components of the solid electrolyte interface on the graphite anode, are not particularly stable to either hydrolysis or to the presence of LiPF6 at moderately elevated temperatures, and they rapidly decompose to generate species such as carbon dioxide, lithium alkoxides, lithium fluorophosphates, and oligoethylene oxides or ethers, and also lithium alkoxides. So this is, once again, many of the species that have been reported by other researchers in the literature as being components of the anode SEI. So this offers an explanation as to why the SEI is more complicated than what is generally, which is observed from the initial reduction reactions, is that the species that are initially generated, which are lithium ethylene dicarbonate and lithium carbonate, aren't particularly stable under the conditions of the battery. They decompose and generate other species. However, somewhat surprising to us, with all of these different reactions that we had done, we did not observe any lithium oxide. And lithium oxide is a frequently observed or frequently reported decomposition product or component of the anode SEI. So with this in mind, we wanted to go back. We wanted to look and study the pure thermal decomposition of pure lithium ethylene dicarbonate. So we already went over basically the reactions of LiPF6, the acid-induced decomposition reaction, since LiPF6 dissociates into PF5, and that is a strong Lewis acid. But what about the actual thermal decomposition of pure lithium ethylene dicarbonate? So we went back and looked at this by utilizing thermogravimetric analysis. And what you can see is if you take pure lithium ethylene dicarbonate and start to heat the sample, we have 3 different stages or 3 different steps in terms of the overall thermal decomposition of this material. And so in an effort to go back and understand each of these steps and how this material thermally decomposes, we went back and we stored a sample of lithium ethylene dicarbonate at 300 degrees, so above this particular thermal transition. And then we stored another sample at about 600 degrees above the second thermal transition, and then characterized the material. And what we can see is we start off with lithium ethylene dicarbonate, we heat it to 300 degrees, and basically the lithium ethylene dicarbonate quantitatively decomposes. And we have 2 different peaks. One is lithium carbonate here on the right-hand side, and then on the left-hand side, it's characteristic of lithium carboxylates. So this was always something that was kind of confusing to me, is that it's very easy to understand how you can generate lithium carbonates and lithium alkyl carbonates from the decomposition of alkyl carbonate species, but I was always perplexed as to how lithium carboxylates are generated, which had been frequently reported. But yet here we see fairly high concentrations of the lithium carboxylates. Now, if we continue heating the sample up to 600 degrees, the lithium carboxylates decompose, and we end up with only lithium carbonate as the only species. So with this in mind, we went back, and my postdoc working with me at the time utilized an instrument in our department, which is a TGA with IR. Now, this is a great instrument where you can take and heat up the sample, and not only can you look at all the weight loss that's occurring, but you can also look at the gases and characterize the gases that are being given off by IR spectroscopy. And the top plot here is the Gram-Schmidt absorbance, which is basically an integral of all of the IR spectrum as a function of temperature. And this looks pretty similar to the TGA curve that we saw on the last slide. And then in addition, if we look at the overall gases that are evolved, the IR spectrum that are spectra that are evolved as a function of temperature, what we see is at low temperature, all we're observing is the residual solvent, dimethyl carbonate, evaporating. Then as we increase the temperature, we first start to observe just ethylene. And then at slightly higher temperatures, we observe ethylene and CO2. And then finally, at very high temperatures, we observe the 3-pentanone, which is characteristic of the decomposition of the carboxylates. So we put all this together, we propose a mechanism for the overall thermal decomposition of lithium ethylene dicarbonate. And what we see is that we start off with lithium ethylene dicarbonate, which once again is the primary component of the anode SEI. The lithium ethylene dicarbonate evolves ethylene to generate this peroxycarbonate species, which is inherently unstable. This peroxy species can have 2 different decomposition mechanisms. First, it can evolve CO2 to generate lithium carbonate. Secondly, we can do an addition reaction of ethylene into the lithium peroxycarbonate to generate this lithium carboxylate species, which, as you can see, has a new carbon-carbon bond. The lithium carboxylate species can decompose via evolution of 3-pentanone to generate lithium carbonate. And then finally, at very, very high temperatures, the lithium carbonate decomposes via a known mechanism of evolving CO2 to generate lithium oxide. So this was very pleasing to us because now, in addition to all the other species that we had observed, now we had evidence for the decomposition of the SEI species to generate lithium carboxylates and also lithium oxide. And so with this in mind, we kind of summarize all of these decomposition reactions that we observed. And so first off, during the initial reduction reactions, the initial formation charging cycles of the lithium-ion battery, there are really 2 reactions that are occurring. Ethylene carbonate is being reduced to generate lithium ethylene dicarbonate and ethylene, and LiPF6 is being reduced to generate lithium fluoride. And so one should have a relatively simple anode SEI. However, the lithium ethylene dicarbonate is not stable under the conditions of the battery. It can decompose via hydrolytic or acid-induced LiPF6 or PF5 based acid-induced decomposition reactions to generate fluorophosphate species, lithium alkoxides, oligoethylene oxides, and other ethers, lithium alkoxides, along with lithium fluoride. And you can also have the pure basic thermal decomposition reaction of lithium ethylene dicarbonate to generate lithium carbonate, lithium carboxylates, and also lithium oxide. So the initial components on the graphite, the initial components of the SEI that are generated during the first cycles are not stable. And the reason the SEI is so complicated in the lithium-ion battery is because the initial species are not stable and they decompose to generate a very complicated mixture of species. Now, with this in mind, we try and go back and we propose a mechanism for the overall SEI thickening. So last year, there was a paper manuscript published in Current Opinions of Electrochemistry when they proposed two models for the thickening of the SEI. First off, there's electrical tunneling through the SEI to cause reduction of more electrolyte species. And the other one was that the SEI that's initially generated is still somewhat porous, which allows some of the electrolyte to diffuse into the surface and get reduced and therefore thicken the SEI. We now propose a third alternative mechanism, which is that the initial SEI is generated, which is a nice thick passivating film composed of lithium fluoride and lithium ethylene dicarbonate. However, upon aging or exposure to low concentrations of water or low concentrations of impurities, which may happen in many research cells that are done under very dilute solvent conditions, the LEDC decomposes. And one of the most important aspects of this decomposition reaction is that many of the decomposition products are gases, such as CO2, or electrolyte soluble species, such as oligoethylene oxides or fluorophosphate species, and that by parts of the SEI dissolving into the solution, the SEI becomes more porous. Now that the SEI is more porous, it allows new electrolyte to come into the surface and be reduced and result in an overall thickening of the SEI. Now, one of the pleasing things with this overall model is that many researchers have reported that the inner SEI of lithium-ion batteries is more inorganic in nature, and the outer SEI is more organic in nature. And this model, where the SEI decomposes, becomes porous, and then allows additional electrolyte reduction, is consistent with this overall model to generate an inorganic rich inner SEI and an organic rich outer SEI. So with that in mind, that brings us to electrolyte additives. And how do electrolyte additives affect the overall structure and stability of the anode SEI? So two of the most frequently utilized electrolyte additives are vinylene carbonate and fluoroethylene carbonate. And in general, these additives have been reported to generate polymeric species on the surface, which results in the generation of a more stable anode SEI. So we went back and tried to characterize these things with the same combination of techniques. And first off, it's important to note that if you look at electrolytes which contain FEC or VC, and we start to charge the samples and then discharge the samples, what you can see is that both of these two species are reduced prior to when the reduction of EC occurs, which then generates the SEI. So with this in mind, we went back and we characterized the surface films for the graphite anode for the standard electrolyte formulation compared to electrolytes with VC and FEC. And what we saw to our surprise is that basically in the case of the VC and the FEC, we utilized HAXPIS, which is high energy X-ray photoelectron spectroscopy. In this case, we use higher energy irradiation, which goes deeper into the sample. And what we see with the standard electrolyte is that all three different energies, we see basically the same spectrum. What that tells us is the SEI, the composition of the SEI, or I should say, sorry, that the SEI is thicker than the greatest depth of penetration of the HAXPIS. However, in the case of VC, what we start to see at higher energies is the graphite, the peak for graphite itself. This is the carbon spectrum. And we see the same thing in FEC, though not quite as much. Now, what was surprising with this is it's pretty well known that with when you utilize vinylene carbonate or fluoroethylene carbonate, you end up generating an anode surface film which is more resistive, which has higher impedance. And usually people attribute this to a thicker SEI. However, what we see here is in the presence of VC and FEC, we see a thinner SEI, but yet it's still more resistive. But what that tells us is that the VC and the FEC are changing the composition of the SEI, and that lithium ion conduction through the SEI is dependent upon the composition of the SEI. Oh, I'm sorry. And once again, in terms of VC, when we do our standard XPS analysis, we see predominantly lithium carbonate with much lower concentrations of lithium ethylene dicarbonate. And in the case of FEC, we also inhibit lithium ethylene dicarbonate generation and see a lot of lithium carbonate and lithium fluoride. So clearly the composition here is changing, and it's becoming richer in lithium carbonate. So if we go back and do the OEMS analysis in collaboration with Hubert Gasteigger at TU Munich, what we observe is we see a significant reduction in ethylene evolution, ethylene generation for this electrolyte with VC, and also we start to see carbon monoxide for the first time. With the standard EC-based electrolytes, we do not observe any carbon dioxide. However, with VC, we see significant concentrations. If we go back and do the same analysis, OEMS, or Hubert did the same analysis with OEMS, with the FEC-based electrolyte, we observe the same thing, where the amount of ethylene being observed is significantly reduced. The amount of CO2 being observed is increased significantly. And also we see hydrogen, H2, being evolved in the case of the FEC. So we went back and tried to study these same materials with the lithium naphthalene reduction. And I remind you that in the case of the ethylene carbonate-based solvent, we do reduce this compound with lithium naphthalene, and we generate lithium ethylene dicarbonate and ethylene gas in virtually quantitative yields. However, when we go back and do this reaction with vinylene carbonate, we observe carbon monoxide and an insoluble polymer. The polymer was not surprising at all. However, the generation of carbon monoxide was, because in the results from Hubert Gasteigger's online electrochemical mass spectroscopy, we observed carbon dioxide, not carbon monoxide. Now with FEC, we observed the same carbon monoxide along with a lot of lithium fluoride and the same insoluble polymer. Now what was interesting with this is that we went back, we realized that we could add a sub-stoichiometric amount of lithium naphthalene to VC and get all the VC to polymerize. While in the case of the FEC, we needed one equivalent of lithium naphthalene per one equivalent of FEC to polymerize the entire reaction. What that tells us is this reaction is catalytic, VC reaction is catalytic, and the FEC reaction is stoichiometric. What it also tells us is we have a large excess of lithium naphthalene in the case of VC. And so we are indeed generating carbon dioxide initially. However, that carbon dioxide is being reduced to generate lithium carbonate and also carbon monoxide. So we went back and we did a collaborative effort with Professor Claire Gray. And basically what we observed what she helped us with and did solid state NMR spectroscopy, we were able to propose an overall reaction mechanism for the reduction of vinylene carbonate to generate polyvinylene carbonate. But also what was interesting is we were able to characterize this exact same polymer from fluoroethylene carbonate, which was quite surprising. But then when we went back and did a more detailed investigation of the fluoroethylene carbonate, what we noticed is that the fluoroethylene carbonate under very dilute conditions initially generates vinylene carbonate along with lithium fluoride and hydrogen, which was observed by Hubert Gasteigger by OEMS, and that then the vinylene carbonate polymerizes to generate poly-VC. So it's very interesting that these two very common additives, vinylene carbonate and fluoroethylene carbonate, have fairly different reaction mechanisms, but yet generate very similar products. So basically, in terms of what's the SEI generated, what's the structure of the SEI generated with the FEC and VC? Well, basically, in the case of the VC electrolyte, what we generate is a fair amount of lithium fluoride, still high concentrations of lithium carbonate, and also poly-VC. And in this case, since the polymerization mechanism is a catalytic polymerization mechanism, we anticipate significantly higher molecular weight poly-VC and much more heavily cross-linked poly-VC. While in the case of the FeC electrolyte, what we observe is significantly higher concentrations of lithium fluoride, since the reduction of FeC itself generates lithium fluoride as the first step. And then lower concentrations of the poly-VC, because basically we have a stoichiometric reaction, polymerization reaction. At the same time, since we have the similar decomposition mechanism where FeC also evolves CO2, the CO2 is reduced to generate lithium carbonate, and we would expect to still have high concentrations of lithium carbonate. Now, what's not clear is what's the aspect of the SEI that's imparting the improved stability. Is it the presence of the poly-VC, or is it the higher concentration of the lithium carbonate? Because we know that lithium carbonate is significantly more stable than the lithium alkyl carbonates, and previous investigations by Martin Winter and Doron Auerbach had utilized CO2 as an electrolyte additive, where they pumped up cells with CO2 gas, and they observed a significant extension of the calendar life of the lithium-ion batteries and a more stable SEI. And so it's still, I would say at this point, unclear which is more important, the presence of the poly-VC or the presence of the lithium carbonate. But either way, we've developed a better understanding of what how compositional changes to the SEI can result in improvements in performance. And now we can go back and try and systematically make an SEI which has just the lithium carbonate or just the polymer to see which one of these has a larger impact on the overall calendar life performance. So this brings us to the next section, which are silicon electrodes. So the silicon electrode has significantly greater capacity than does the graphite, almost 10 times. However, the lithiation of the silicon is accompanied by a 300% volumetric expansion and contraction. And this generates a significant problem due to the mechanical stress of the electrode laminate, cracking of the silicon particles, and electrolyte consumption with the generation of a constant new SEI on the surface of the largely expanding and contracting silicon particle. So the SEI components are very similar on graphite and silicon. However, the SEI components are less stable on silicon anodes upon cycling. And so what we wanted to go back is try and understand this difference between ethylene carbonate and fluoroethylene carbonate on silicon anodes. And we did this focus on fluoroethylene carbonate because various literature reports have suggested that fluoroethylene carbonate is the best anode SEI film forming additive for silicon anodes. So if we go back and we do these an investigation of binder-free silicon electrodes, and once again, similar to our previous study with graphite, these investigations were conducted in a simplistic two-component electrolyte, LiPF6 and EC, or LiPF6 and FeC, and no other components. And what we observe is that we see significantly better capacity retention with the FeC-based electrolyte than we do with the EC-based electrolyte. So what we want to do is go back and try and characterize and understand how these changes in performance relate to the changes in the solid electrolyte interface. And so if we look at the TEM images of the nanoparticle silicon, what we see is upon cycling 1, 5, and 20 cycles, is after the first cycle, we start to see, the particles still look okay, although there's a fair amount of damage. We start to see high concentrations of oxygen and fluorine on the surface of the silicon. As we continue cycling them, basically the particles kind of turn to mush. And basically what were nice nanoparticle silicons all kind of turn into one big mashed particle, which contains high concentrations of carbon and oxygen. What this suggests is that basically the SEI and the silicon particle are becoming combined together and basically just making one homogeneous mixture. In the case of the LiPF6 with FeC, we start to cycle the electrodes, and initially we start to see little particles on the surface of the silicon, nanoparticles. And when we do the analysis of these nanoparticles by EDX, with these nanoparticles have very high concentrations of fluorine. And while we weren't able to state this originally when we published this paper, the particles are very consistent with nanostructured lithium fluoride, which we'll see later on in the section on lithium metal anodes. But nonetheless, as we continue cycling these from 1 cycle to 5 cycles to 20 cycles, we can still see that the silicon particles are largely retained, and yet there's a surface film around these particles, which is clearly the generation of some solid electrolyte interface. Also, much like what we observed in the case of the LiPF6 and PC-based electrolytes, this solid electrolyte interface is very grainy, with clearly very small little nanostructured particles on the surface. It's also important to recognize that in the case of the SEI generated with LiPF6 and FEC has a much higher concentration of fluorine, about 32%, almost 33%, and compared to EC at 3.5%. And as I said, many of these nanostructured species in the surface film are consistent with nanostructured lithium fluoride. So if we go back and we look at the silicon surfaces, once again utilizing HAXPS, which is high energy X-ray photoelectron spectroscopy, which allows us to depth profile basically, so we can look at deeper information. And we look at the cells cycled with an EC-based electrolyte, or the pure FEC-based electrolyte, or EC with 15% FEC as an additive. What we see is with the EC-based electrolyte, after the first cycle, we see basically lithium ethylene dicarbonate throughout the entire depth of the SEI. However, after 5 cycles, we only see the lithium ethylene dicarbonate on the outside, while on the inside, clearly the lithium alkyl carbonates have decomposed to generate lithium carbonate and lithium alkoxides in other species. Alternatively, when we have FEC around, we see a significant reduction in the generation of the lithium alkyl carbonates. And also, as we go from 1 cycle to 5 cycles, and we go with the depth profiling, the composition of the SEI doesn't change. What this tells us is that the SEI, the inner SEI, in the case of EC-based electrolytes, is evolving. The SEI is not stable. It's changing. It's decomposing. While in the case of the FEC-based electrolyte, the SEI isn't changing on the outside or on the inside, which suggests that the SEI itself is stable and doesn't change. So what this suggests is the surface area changes on silicon accelerate the decomposition of lithium ethylene dicarbonate, and this contributes to the poor performance of silicon anodes. Now, if we look at the overall difference in the performance of FEC versus EC, we can see that EC ethylene carbonate reduces to generate lithium ethylene dicarbonate, while FEC reduces to generate lithium fluoride and poly VC. And that basically what we have with the EC-based electrolyte is a lithium ethylene dicarbonate rich SEI. However, upon additional cycling, the lithium ethylene dicarbonate decomposes, and we end up with an inner SEI, which is rich in both lithium carbonate and lithium fluoride, and an outer SEI, which is rich in lithium ethylene dicarbonate. While in the case of the FEC-based electrolyte, we generate an SEI which is composed of lithium fluoride and lithium carbonate and poly FEC, and after multiple cycles, this SEI doesn't really change. It's stable. So the SEI components with FEC are more stable and decompose at a slower rate, and that's why you get the improved performance, because of the increased stability of the SEI and the increased stability of the SEI components, in particular the lithium carbonate. So if we revise the overall model of evolution, of SEI evolution on silicon, we start off with the EC-based electrolyte. We have lithium fluoride, a lot of lithium ethylene dicarbonate. As we delithiate the silicon shrinks. And as it shrinks, the mechanical damage occurs to these rigid solids. And basically they break up into smaller particles. And then they are exposed to the electrolyte, which causes them to be rapidly decomposed to generate the other species via the same LiPF6 induced decomposition reactions that we saw on graphite, but at a much accelerated rate. As we relithiate the surface of the silicon, we expand again. We have once again the inner SEI, which is predominantly composed of lithium carbonate and lithium fluoride, and we generate a new outer SEI resulting from the generation of the lithium ethylene dicarbonate, more new lithium ethylene dicarbonate. While in the case of the FEC, we have the poly VC or the poly FEC on the surface, along with high concentrations of lithium carbonate and lithium fluoride. As we delithiate the anode, basically the flexibility, the mechanical flexibility of these polymers allows the SEI to flex and then come back without damaging the rigid inorganic SEI components. And then as we relithiate, basically the integrity of the SEI film stays, and we have a great overall stability. So with this understanding, how could we go back and design now a more stable SEI on the silicon anode? And so what this brings us back to is to another investigation that we were doing, which was to try and understand the effect of binders on anode materials, and in particular, the effect of binders on silicon anodes. So all lithium-ion batteries are composed of electrodes, electrode laminates, which contain an active material such as graphite or silicon, along with 5 or 10% of a binder, which is frequently some polymer. The most frequently used binder in lithium-ion batteries is PVDF, polyvinylidene difluoride. However, initial investigations of PVDF with silicon anodes showed that PVDF did not work well with silicon anodes. And instead, what was utilized was polyacrylic acid or carboxymethylcellulose binders, and these ones worked very well. And so we wanted to go back and try and understand why these different binders work so well with silicon anodes, while they're fairly comparable with graphite anodes to the PVDF. And what we see is if we take the silicon with PVDF, and we have the fresh electrode, we basically just see the IR spectrum of PVDF. We charge the battery, we start to see a lot of lithium alkyl carbonates, but then after the first cycle, we start to see a lot of lithium carbonate, and we see more and more and more lithium carbonate after the 10th cycle, which one is consistent with this decomposition of the lithium ethylene dicarbonate to generate lithium carbonate and consumption of more electrolyte species and poor efficiency of cycling. However, in the case of the silicon PAA electrode, we start off, we have the polyacrylic, we start off with the fresh laminate, and we look at the lithiated PAA. And first off, what we can notice is upon making the laminate, the IR spectrum of the polyacrylic acid changes, and we have what is effectively lithiated polyacrylic acid. Now, also, as we cycle this, we see some lithium alkyl carbonates, we see some lithium carbonate, but the changes with additional cycling are much, much less for the polyacrylic acid sample than in the PVDF sample. What this brought us in mind is, once again, from the background of physical organic chemistry, which was what my training is, though if polyacrylic acid stabilizes the lithium, the silicon anode so well, what about something like citric acid? These are structurally similar. Do you really need the polymer? And what we observe is that basically if we take the fresh electrode with the polyacrylic acid versus the fresh electrode with citric acid, we basically see very, very similar surface films initially. And also, surprisingly, if we compare the cycling performance here, the capacity retention, with silicon with polyacrylic acid versus silicon with citric acid, which once again is not a polymer, we see very, very similar cycling performance. What this suggests is that somehow the citric acid is doing something similar to the polyacrylic acid. And once again, what we can see is that we start off with the silicon, the PAA, we generate lithiated polyacrylic acid, which stabilizes the SEI. And with the citric acid, we do the same thing. We generate lithium citrate, and the lithium citrate inhibits the overall evolution of the SEI. So now what's happening here is if we take silicon and we take silicon and add citric acid to it, we see that we can observe the citric acid binding to the surface of the silicon nanoparticle. We see present there. And if we look at the thermogravimetric analysis of this citric acid with silicon particle modified by citric acid, and as we heat the sample, we observe weight loss consistent with basically the loss of a monolayer of citric acid. So what we believe is happening here is we take our silicon particle, we incorporate the citric acid, and we're basically making a monolayer of citric acid on the surface of the silicon. And this monolayer of citric acid effectively acts as a pre-SEI. So we already have SEI components. As we lithiate the silicon, we convert the citric acid into lithiated citric acid, which provides significant stabilization. Now, what's interesting with this is that most commercial lithium-ion batteries contain graphite, or many commercial lithium-ion batteries contain graphite with low concentrations of silicon nanoparticles. So we went back to look at how these surface-modified silicon particles perform in graphite anodes, and we see a significantly better capacity retention for the surface-modified silicon nanoparticles compared to the pure silicon nanoparticles. And so once again, in the case of PVDF-based anodes, we have just the SEI getting thicker and thicker and thicker due to the decomposition of lithium ethylene dicarbonate. While in the case of the citric acid, we modify the surface of the silicon to make citric acid monolayer. Then this citric acid monolayer is converted on the first cycle to lithium citrate. We observe some additional electrolyte deposition and decomposition on the surface, but the amount of additional electrolyte deposition is very, very small. And so our modified generation of the SEI for these pre-SEI silicon electrodes with citric acid is we basically take the silicon, we modify the surface with citric acid. Upon lithiation, we generate the lithiated citric acid, along with some lithium alkyl carbonates and lithium fluoride. However, upon delithiation, the citric acid pre-SEI helps to retain the structure of the SEI and inhibit the further decomposition of the SEI and slow the overall thickening of the anode solid electrolyte interface. So with this, it brings us to the final topic of today's lecture, which is how important is morphology to the performance of the SEI. So as I said earlier in the presentation, when we have graphite with 1.2 molar LiPF6 and EC, we generate an SEI which is quite smooth and it's quite uniform in terms of its appearance. However, when we go to the SEI, which is generated with 2.6 molar LiPF6 and PC, we have a very, very grainy SEI. And in terms of the grainy SEI, we have a high concentration of lithium fluoride and a low concentration of lithium alkyl carbonates. While in the case of the smooth, uniform SEI, we have a high concentration of lithium ethylene dicarbonate and a low concentration of lithium fluoride. Now, if we look at the silicon nanoparticles that we just went over, the silicon nanoparticles have these nanostructured lithium fluoride particles on the surface during the first charging cycle. And so what we wanted to go back and say is, well, you know, how important is the morphology of the SEI? We've spent a lot of time trying to characterize and understand the components of the SEI, but what's the role of the overall morphology of the SEI also? And so while there have been many, many manuscripts discussing the composition, the morphology has received far less attention. And so with this, we went back to look at lithium metal anodes, which is, you know, as I said in the first lecture, one of the holy grails of the lithium ion battery is to develop the lithium metal anode, which has much higher capacity. However, there are numerous problems with the lithium metal anode. First off, we have an unstable SEI. We have poor Coulombic efficiency. We have poor capacity retention, and we frequently generate lithium dendrites and mossy lithium, which can lead to shorts and lead to lost capacity. However, electrolyte formulations have been shown to significantly improve these performance, as shown in these following publications here. And also, it's been reported that if you have lithium fluoride on the surface of the lithium metal, that this can also significantly improve the performance of lithium metal anodes. So with this in mind, we went back and tried to start understanding the mechanisms and the role of electrolyte in the cycling performance of lithium metal anodes. And so we started off our investigation with lithium symmetrical cells. And if we use the LiPF6 electrolyte with, once again, now we're in carbonate solvents, EC, EMC, 3 to 7, we cycle them for a few cycles and the cells die. Same thing occurs with LiBF4. However, if we use lithium difluorooxalato borate, this species here, we basically can cycle the cells for 2,000 hours. Very, very long time. However, if we use LiBF4 plus LiBob, which is basically a combination of two species, which are the same components of lithium difluorooxalato borate, basically they're half and half, we also see the cell die very rapidly. And if we use the LiBob electrolyte, lithium bisoxalato borate, once again, the cell dies very rapidly. And so we were really confused as to why the lithium difluorooxalato borate has such good cycling performance, where especially this very, very similar electrolyte formulation has very poor cycling performance. So we went back and in addition to using lithium symmetrical cells, we went back and built some copper lithium iron phosphate cells. Now these cells are really nice because the lithium iron phosphate is very low potential cathode material, so it minimizes oxidation of the electrolyte. We're in situ generating lithium metal by plating it on the copper, and so therefore there's no initial reduction of electrolyte when you build the cell. So you build the cell and there's no reaction until you start trying to charge it. And there's a limited lithium source. And this is really nice in terms of research because basically there's not a lot of lithium present in these cells to be cycled back and forth. And so if you're losing lithium during the process, the cells will fade very, very rapidly. And so you can get pretty rapid results. And so with this in mind, we went back and we looked at these same series of electrolytes. And what we see is the lithium difluorooxalato borate cycles very, very well, lasting almost 50 cycles, while all of the other electrolytes die before about 10 cycles. We also see a significantly better efficiency for the lithium difluorooxalato borate electrolyte, while the other electrolytes all have very, very poor efficiencies. Also surprising to us was that with the lithium difluorooxalato borate electrolyte, we see very, very low impedance after the 10th cycle, while for all of the other electrolytes, we see much, much higher impedance. So what this suggests is that basically it's very consistent with our lithium metal symmetrical cells, and that the lithium difluorooxalato borate has much, much better cycling performance and much lower electrochemical impedance than all of the other electrolyte formulations. So we went back and we studied the materials by X-ray photoelectron spectroscopy to try and see the difference. And while there's a lot of information on this slide, the main thing we want to focus on is the lithium difluorooxalato borate and the LiBF4 plus LiBob. Now we notice here is after the first plating cycle, these are the carbon spectra, the two SEI films are very similar for the lithium difluorooxalato borate and the structurally analogous LiBF4 plus LiBob electrolyte. However, after 10 cyclings, the structures are very, very different. And in fact, the structure with LiBF4 plus LiBob looks much more so like the LiBob electrolyte. Now, the same thing is the case with the fluorine spectrum and also the boron spectrum. So as we start off, and basically, initially, the boron spectra are very similar for the LiBF4 plus lithium difluorooxalato borate. However, after 10 cycles, the spectra are very similar for the LiBob and the LiBF4 plus LiBob. And the same thing is the case with the oxygen spectrum, where we start off and initially the SEI is similar, but then after 10 cycles, now the SEI changes for the LiBF4 plus LiBob and is more LiBob-like. So what this tells us is that while initially we're maybe generating a similar SEI, in the case of the lithium difluorooxalato borate, also we see very small changes to the overall SEI, which is consistent with a stable SEI generation. But nonetheless, the composition here is pretty similar. So since the compositions were pretty similar, there must be something else that's overall being the major effect in terms of improving the overall stability of the SEI. And so with that, we went back to TEM, transmission electron microscopy. And with the EC EMC electrolyte with LiPF6, what we see with only 15% of the plating of lithium, we see very non-uniform lithium. The lithium's kind of all over the place. We see a lot of dendrites. We see a lot of lithium with mossy lithium. There's not a very uniform plating of the lithium metal. This does not look good. When we go to the LiBF4 plus LiBob electrolyte, initially we start to see these really large 100 nanometer particles that are predominantly lithium fluoride. But still, we see a lot of non-uniform, more uniform lithium plating, but not particularly uniform. It's still kind of not a very good lithium metal coating. However, when we go to the 1.2 molar lithium difluoroxylated borate electrolyte, now what we see is very, very uniform plating of the lithium metal. And throughout the entire surface of the lithium metal, we see all these tiny little particles, which are consistent with lithium fluoride from EDX analysis. And see, we also see a very uniform layer covering all these lithium fluoride particles, which is consistent with a combination of lithium carbonate and lithium oxalate. So it appears that we're generating that lithium difluoroxylated borate is decomposing to generate these nanostructured lithium fluoride particles that are surrounded by an amorphous layer of lithium carbonate, and that somehow this lithium fluoride, nanostructured lithium fluoride, is allowing these materials to have very uniform lithium plating. Now, with this in mind, another electrolyte formulation which had been reported to be very good for lithium metal anodes is electrolytes which contain fluoroethylene carbonate, FEC. And once again, if we build our same copper LFP cells, what we see is a standard EC EMC electrolyte with LiPF6. The performance fades very, very rapidly. We add 10% of FEC, we see a much better capacity retention. And we go to pure FEC, we see dramatically better capacity retention, fairly similar to what we saw for the lithium difluoroxylated borate, and also much higher capacity, much higher efficiencies. So we see fairly similar performance for the FEC electrolyte that we did for the lithium difluoroxylated borate electrolyte. So when we went back and looked at the TEM images again, we were happy to see that basically in the case of the FEC-based electrolyte, we see very similar nanostructured surface films containing nanostructured lithium fluoride particles. So once again, this is consistent with the fact that if we generate these nanostructured lithium fluoride particles, which once again are covered by a layer of lithium carbonate, that somehow this is affording us good lithium plating capabilities. So what are the similarities between these two electrolyte formulations, lithium difluoroxylated borate and FEC containing electrolytes? Well, first off, we've gone back and we've characterized the fundamental reduction reactions of both of these components, FEC and lithium difluoroxylated borate, by lithium naphthalide reduction reactions. And what we see is that both species generate high concentrations of lithium fluoride along with CO2, and that the CO2 is further reduced to generate lithium carbonate. They also, in the case of FEC, generates poly-VC, and in the case of lithium difluoroxylated borate, generates these oligoborates. And so basically we believe that this nanostructured lithium fluoride results from the simultaneous generation of lithium fluoride and CO2, which then generates lithium carbonate from the same molecular species, which results in an overall capping of these lithium fluoride particles to trap them as lithium fluoride nanoparticles. And there's been some computational investigations which suggest that there's high lithium ion conductivity along the lithium fluoride lithium carbonate interface. And so if you generate a large number of nanostructured lithium fluorides particles, which have high surface area, and then surround these with a lot of lithium carbonate, what you'd expect is high lithium ion conduction along all these interfaces between the lithium fluoride and the lithium carbonate. So how do we propose a model to this? And so basically, once again, the lithium difluoroxylated borate, or the FEC, we generate the lithium fluoride nanoparticles with a coating of the lithium carbonate. And this results in very good lithium plating, uniform lithium plating from these cells. While in the case of the LiPF6 based electrolytes or the LiBF4 plus LiBob electrolytes, we generate very large lithium fluoride particles, and we have additional electrolyte decomposition, and we have non-uniform lithium plating. So in an effort to try and explain this, this can be partially explained at least by what's observed commonly in ultra micro electrodes. And that when you have an insulating phase which is very small, such as our lithium fluoride nanoparticles, the diffusion gradients above the surface overlap, resulting in uniform electric field gradients across the entire surface, and therefore uniform plating of the lithium metal. However, if we have larger insulating phases, so larger particles of lithium fluoride, what these result in is non-uniform electric field gradients across the surface of the lithium metal and non-uniform plating, and therefore dendrite formation and poor cycling performance. So in summary here, the initial SEI is a mixture of lithium ethylene dicarbonate for graphite anodes with LiPF6 and EC-based electrolytes. The initial SEI is a mixture of lithium alkyl carbonates, such as lithium ethylene dicarbonate and lithium fluoride. The composition of the SEI is dependent upon the electrolyte solution structure. So if you increase the salt concentration, you typically increase the concentration of lithium fluoride. As I mentioned in the previous presentation, there's a lot of interest in very high salt concentration electrolytes, such as the WISE electrolytes, the water and salt electrolytes. In part of the reason that there's so much interest and there's so different behavior for these high salt concentration electrolytes is that by changing the salt concentration, you're changing the surface film that's generated, and that's changing the overall performance of the electrolyte. In terms of the aging of standard lithium-ion battery electrolytes, the instability of the SEI components, in particular the instability of the lithium ethylene dicarbonate, contributes significantly to SEI evolution and the degradation of the SEI. The electrolyte additives, such as FEC, fluoroethylene carbonate, or vinylene carbonate, they alter the SEI composition and they improve the overall stability of the SEI. At this point, it's still unclear as to whether they improve the stability of the SEI due to the higher concentration of the lithium carbonate or due to the higher concentration of the polymeric species on the surface. But nonetheless, further investigations will likely lead to a better understanding of which of those two components is the primary contributor to the improved stability. The initial composition of the SEI is similar on both graphite and silicon and lithium for the same electrolyte formulations. However, the stability is different. So in the case of graphite, where you do not have a very large volumetric change, the SEI is stable, or an SEI composed of lithium ethylene dicarbonate is stable. However, on species such as silicon and lithium, where you have large volumetric expansions and contractions for silicon, or in terms of lithium metal, you're plating and stripping and plating and stripping and plating and stripping. So the whole surface is changing. In those cases, the presence of the lithium ethylene dicarbonate is not stable, which leads to subsequent decomposition of the lithium ethylene dicarbonate and subsequent further reduction of reactions of the electrolyte, consumption of the electrolyte, and poor electrochemical performance. And then finally, the morphology and nanostructure of the solid electrolyte interface components may be as important to the composition, may be as important as the composition of the SEI. And so in terms of the future investigations of the solid electrolyte interface, so in terms of the community understanding better, one of the real keys with this system is to really understand the role of the solution structure and also desolvation in SEI formation and cell impedance. So what I really didn't mention is that basically you have a solvated lithium cation, as we mentioned in terms of the differences with propylene carbonate-based electrolytes. However, these solvents must be stripped from the solvents before they can be intercalated into the graphite or plated onto the lithium metal. And there's a very large energy barrier for this desolvation effect. And how the role of this desolvation and the importance of this desolvation is something that really needs to be better understood in lithium battery electrolytes. Which this also brings up another really important fundamental chemistry topic that's very important to the battery industry, which is what we need to develop a better understanding of why slow formation cycling is required. So this is something that I haven't really mentioned in the previous presentations, but lithium-ion batteries must undergo something referred to as formation cycling. So after the cell is built, the lithium-ion battery manufacturers will undergo a very sophisticated process, which is usually privately held by the company. And it usually takes about a week, where they slowly charge and discharge the battery multiple times. And during this formation cycling, they generate the reason that they do the formation cycling is to generate a good anode SEI. However, why you need to do the slow formation cycles is not very well understood. And from an industrial perspective, taking a full week of battery cycling time to cycle all these cells is an extremely expensive process. And so if they can develop a better understanding of what is happening to the structure of this SEI because of the slow formation cycling, they would be able to perhaps avoid such a long time process of the formation cycling. Most likely, this slow formation cycling is not changing the composition of the SEI. It's more likely that slow formation cycling is changing the morphology of the SEI, or at least from preliminary investigations in our lab. And what this brings up once again is what's the overall role of the morphology in SEI function. So in Pelled's original depiction, he showed this mosaic where he had a whole bunch of chunks of different components and showing lithium ion conduction along the grain boundaries. So is this really the primary mechanism of lithium ion conduction? From our results on lithium metal anodes where we see the nanostructured lithium fluoride, I would say it's somewhat consistent with this. And so it may be that the best way, we must understand how the lithium ions are transported through this SEI and what is really the role of the bulk materials, the lithium fluoride or lithium carbonate, versus the role of the grain boundaries in terms of the ion transport along these materials. And then finally, in terms of the cathode, there's also cathode surface films. And what's the role of electrolyte in the cathode electrolyte interface formation and evolution? And that's something that we will go over in the final presentation of this series, which I will get to here shortly. And once finally, I'd like to thank, in terms of this research, the funding agencies that provided the funding for me to conduct this research, which is the US DOE EPSCoR implementation program, along with the BASF Electrochemistry Network. I'd also like to thank all of the graduate students who conducted this work with me and for me, which really include Moon Ying and Moon Ching earlier in my research groups, and then later really include Zach and Sun Young and Teho. And once again, I'd like to thank you for listening to the presentation. And with that, I will stop sharing. And once again, thank you very much. And the final presentation will be on electrolyte reactions with the surface of cathode materials. Thank you very much.